Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 7th, 2025, and we're looking at an ICLR conference paper, When is Task Vector Provably Effective for Model Editing? A generalization analysis of nonlinear transformers, published just over 3 months ago. This paper provides the first theoretical backing for task arithmetic, essentially editing pre-trained models by adding or subtracting task vectors, which are the model's fine-tuning updates. It explores why this works for complex transformers, especially for tasks like multitask learning. Alright, so building on this theoretical groundwork, the authors then investigate how these task vector operations perform for out-of-domain generalization. Specifically, how to choose the arithmetic hyperparameters, those lambda_I values, for a new task, TVAS. This table shows that by carefully searching for these lambda weights, say lambda 1 and lambda 2, they achieve a test accuracy, or TACC, of 91.74%. This is impressively close to full fine-tuning on that new task. So, moving from out-of-domain generalization, this next table explores multitask learning and unlearning. Multitask learning is about excelling at several tasks, while unlearning means selectively forgetting one. It shows how the best lambda, that crucial weight for task vectors, impacts accuracies on two tasks, T1 and T2, based on whether they're irrelevant, aligned, or contradictory. This really highlights how task relationships dictate outcomes with task arithmetic. Okay, in this figure 2, gives us a visual for this. Part A is a heat map showing the testing accuracy on that new task, T, for different combinations of lambda 1 and lambda 2 when using the merged model. That's the model after task arithmetic. The green cross marks the best lambda combo. Part B then shows the region where their theoretical condition for generalization, equation 7, holds true, linking theory to practice. Pivoting back slightly from that generalization condition, figure 1 here provides a clear visual for how that lambda weight, the one we apply to task vectors, impacts the merged model's accuracy on two distinct tasks, T1 and T2. We see 3 scenarios: irrelevant, aligned, and contradictory tasks. It really underscores how the relationship between tasks dictates the optimal lambda for multitask learning or even unlearning. Now, looking at Table 3, we see how these lambda weights specifically impact unlearning. It shows Rouge L scores. That's a common metric for text generation quality for 3 tasks, T_HP1, T_HP2, and T_PP when using a full-rank task vector. As lambda becomes more negative to unlearn task T_HP1, its score drops significantly, as intended, but we also see an impact on the other tasks. So, continuing with unlearning, Table 5 here shifts to using a low-rank task vector. That's a more compressed, efficient version of the fine-tuning updates for task T_HP1, this time on the Phi3 small model. We're still looking at Rouge L scores. As lambda gets more negative to forget T_HP1, its score drops significantly. This supports the idea that efficient, low-rank edits are indeed viable for unlearning. Well, to bring it all together then, this work provides that crucial first theoretical justification for why task arithmetic, essentially manipulating those model fine-tuning updates we call task vectors, is effective for nonlinear transformers. The big takeaway is that success really hinges on task correlations and carefully choosing those lambda weights, even when using efficient low-rank methods. That's our look at this study. Thanks for joining AI Research Roundup. I'm Alex.